Hello and welcome to our next lesson. The last time we were in, we had a lesson on inverse trig, which pretty much wraps up most of trigonometry. We have trig ratios, we have regular trig, and we have inverse trig. And now we're actually going to go into some of the applications of it with angle of elevation and depression. So we're going to see a lot of word problems, a lot of scenarios. It's going to be a lot of drawing, and I cannot stress how important it is to draw the diagram correctly and labeling parts correctly. So, angle of elevation and depression can be a little bit confusing, especially angle of depression, and I want this to be very, very clear. We need to pay close attention to that particular part of this lesson, because if you're in, let's say, you are standing in a room, let's actually draw this a little lower, and you're in the same room as, let's say, Shaquille O'Neal. Shaquille O'Neal is a famous basketball player, played for the Orlando Magic. He is a very tall person. He is 7 feet 3 inches. At least that's what it says in his bio. And he is much taller than most the average person. So when we're talking about, let's say this is you, this is the ground, this is you, and this is Shaq. Okay? When we're talking about angle of elevation and depression, we actually have to first start with like a line of sight. Your normal line of sight goes straight. So we make a dotted line to create kind of like what we call a horizon, a horizontal line. Horizontal line, we should know, goes from left to right. Shaq has his own line of sight, and it goes way over your head. Okay? And let's pretend you and Shaq get into a staring contest. When you and Shaq get into a staring contest, you make eye contact with each other, and you create a direct line of sight with each other's eyes. From your perspective, this is your perspective, you create an angle of elevation because your eyes stray away from the horizon, your horizon, to upwards towards the line of sight. So this is your angle of elevation. Okay? Versus Shaq's line of sight, let me actually keep this blue, let's keep this blue here to illustrate that. Shaq's line of sight strays away from his horizon downwards, and it creates his own angle of depression because he's looking down. Angle of depression. And the very important thing to note is the angle of elevation is inside, let's make this blue, inside of this blue triangle. Notice the red, the angle of depression, is not inside that blue triangle. And there is a very important distinction because when we think depression, we automatically think, okay, we are going to put it in this particular part. I want you to know that the angle of depression is not in the same triangle as the angle of elevation. Once again, the angle of depression is not in the same triangle as the angle of elevation. They are in two different triangles. Because if you look, there's a second triangle that gets created here, and the angle of depression has its own triangle to work with. Now, if you want formal definitions for it, or rough definitions, angle of elevation is an angle created upwards from the horizon, from a horizon to a new focal point. A new focal point. So in this particular case, the focal point is Shaq's eyes. From your perspective, the angle of depression is an angle created downwards from a horizon to a new focal point. And this is from Shaq's eyes to your eyes, to a new focal point. So, important thing to take away is that the angle of elevation and angle of depression are not in the same triangles. Even more important is this. These horizons are both horizontal lines, which means these lines are actually, let's do this in purple. Let's make this a little thicker so we could, where is it? There you go. These two lines, these horizons, are actually parallel. And when you have a transversal going through them, we actually create two angles that are congruent. If you remember this, great. We make that z that we've talked about prior, and whenever you make that z, it creates alternate interior angles. If you remember, alternate interior angles are congruent, which means the angle of elevation and angle of depression are in fact congruent to each other. So this is a nice bonus point to kind of address. Let's do this in purple. Put a star next to this. The angle of elevation is going to be congruent to the angle of depression. And this is because they are alternate interior angles. So it's very, very important that we know that they are congruent to each other. There's only one example if you have, for instance, angle of elevation and angle of depression, let's call this alpha, where they actually are congruent to each other in the same triangle. So this is technically the angle of depression here. If this, for instance, they should never be congruent unless it's a 45-degree angle, because it's 45 here, which means this is also 45. That is the only instance where the angle of elevation is equal to the angle of depression and the complement in the same triangle. Other than that, it should always be congruent to each other, but a complement along the same line. So if this was 60 here, this should be 60 here, and it should make sense that this is 30 because you should have 180 degrees total in your triangles. Okay? So, a lot going on with this definition. I cannot stress how important it is, especially for the angle of depression, to understand that they are not in the same triangle. They are also congruent to each other. And we need to be able to identify them. So, first example. It's a word problem. All we're going to do here is draw the diagram of the scenario. You are standing 50 feet away from a building, from your school. So here's the school. We could say this is 50 feet because you are from the base of it. The base is the very bottom. And you're looking up at an angle of elevation. We're going to ignore your height for now. You're looking up at an angle of elevation of 62 degrees. So let's say your height is negligible. Remember, the angle of elevation comes from your horizon, your natural line of sight straight, upwards towards a new focal point. What is the height of the school? So we could say this is 50 feet. This is the height of the school, minus, obviously, we're going to say this is negligible. And we would calculate this by using trig. This is your opposite side. This is your adjacent side because we make a right angle, and that's how we get a right triangle, and we could actually use tangent here. Tangent of 62 is equal to opposite x over 50. And if you want to solve this, awesome. I'm not making you solve it, but this is how you would set this problem up. Drawing the scenario, labeling the sides properly, and then using the proper trig function once the sides are identified. Okay, so this one, we're actually going to draw and solve. Okay, draw and solve. A bird is in a tree, in a 65-foot tree. So let's draw a tree. We know that this is 65 feet. And the bird is at the very top of it. And it sees a worm on the ground. So here's your worm. At an angle of depression, so the natural line of sight for this bird is to go straight, but it's looking downwards at the worm. Remember, the angle of depression starts at the horizon, goes downwards to a new focal point, and this angle that gets created is 22 degrees. What's important here is that we actually have a right triangle in this part of it. Here's your triangle. We could actually transfer this 22 degrees down to that angle, the angle of elevation. If we consider this as a perspective from the worm, it is looking up at the bird at an angle of elevation. So we could actually say that this is 22 degrees. And if you remember, angle of elevation and angle of depression are congruent. So we can now have this scenario. We have, from this perspective, we have the opposite side, and we are actually looking for the direct distance between the bird and the worm. It should say what is the direct distance to the bird, to the worm. Oops, to the worm. So we want to know how far it has to fly to get the worm. So this is the hypotenuse. And now we could actually solve. So this is opposite and hypotenuse, which is sine. So we take the sine of 22 degrees is equal to opposite 65 over x hypotenuse. Do our little trick where you say x is equal to 65 over the trig function, or the trig value. And then we calculate. 65 divided by the sine of 22, and we get, that L5 is not supposed to be there. 65 divided by the sine of 22, and we get 173.5, let's say round to the tenths. Sorry, what was it? 173.5. 173.5, we're measuring this in feet. And that is how we would use this in the real world, a direct application of trigonometry. All right, we're gonna have a lot of scenarios for this, so please come in with your questions if you have any, and I'll see you in the next one. Bye.